The General Electric T700 is arguably the most successful turboshaft engine ever created. It powers a variety of helicopters like the UH-60 Black Hawk, the AH-1Z Viper, and AH-64 Apache, among about a dozen more aircraft types, with the most advanced variants like the CT7-8A7 producing up to 3,000 shaft horsepower. We're going to examine this engine's design and some of its unique features that allow it to operate in dust, sand and snow with minimal performance loss or damage, and reveal why this engine is still relevant today, more than 50 years after it was first run. Before getting to the T700's design, let's do a quick recap of what a turboshaft engine is and how it works. Understanding this standard design will help emphasize the advanced features of the T700. Like a piston engine, the turboshaft has 4 phases: intake, compression, combustion, and exhaust. Each phase happens in its own section of the engine. Air is drawn in from the front by the compressor rotors. The air is pressurized, which heats it, then fed to the combustion chamber where fuel is added and ignited. As the hot, rapidly expanding gases exit, it spins a turbine. The turbine spins the compressor to keep the cycle going, but also drives the output shaft, which through a series of reduction gears spins the helicopter's rotors. While I think my extremely high-tech and immersive 2D graphics do an okay job at helping visualize concepts, at times like this I often wish I had a real engine with me here to reference. But since I don't have a spare T700 turboshaft lying around in my backyard, Stirlingkit provided me with this model of a T700, which is going to help me explain this engine. Of course, it didn't arrive like this, it arrived like this, and I got to assemble it, but I'll show some of that later in the video. So, looking here, you'll see several things not captured by my previous 2D illustration. Starting at the compression stage, you can't see the rotors looking in from the front thanks to something very interesting at the intake, which we'll get back to in a bit. Before air enters the compressor, it goes through a variable inlet guide vane, or VIGV for short. This controls how air enters the compressor and helps the engine adapt to different operating conditions. Air then enters the compressor, and the T700 has 6 stages of compression, with each rotor counting as one stage. The overall pressure ratio is 17:1. Each stage compresses the air a bit more and moves it axially, that is, this way. These rotors are one-piece blisk rotors, exactly like shown here, meaning the blades aren't attached separately. The entire rotor is constructed as a single piece. In between these spinning rotors, we have variable stator vanes, which are fixed to the casing and don't spin. The purpose of the stator vanes is to adapt to changing airflow conditions, and the blade angles are changed via an actuator shaft. This assists with more efficient compression, with the rotors adding energy and the stators modifying the airflow for the next rotor stage. This is called an axial compressor, and the 5 axial stages account for a 7:1 pressure ratio. But you'll have counted only 5 rotors, and I said this is a 6-stage compressor. That's because the 6th and final stage of compression uses a centrifugal compressor, a design not much different from what you'll find in your car's turbocharger. This is an impeller with curved blades that, as it rotates, accelerates air outward through centrifugal force, further pressurizing the air before it enters the combustion chamber. It brings the total pressure ratio up to 17:1, meaning the centrifugal stage alone contributes a 2.43:1 pressure ratio increase. Not all gas turbines use centrifugal compressors, since axial compressors can handle higher air mass flow rates, have a smaller frontal area, and can achieve higher overall pressure ratios, making them more efficient. So why does the T700 use 5 stages of axial compression followed by 1 stage of centrifugal compression? Simply put, to get the best features of both. Even though axial compressors can achieve higher pressure ratios, they achieve less pressure increase per stage, meaning they usually need at least 10 stages, making the engine very long. So instead of using 10 plus stages of axial compression, combining 5 axial stages with 1 centrifugal stage makes the engine much shorter. Critically important for the helicopters it powers, while also bumping total pressure ratio up to 17:1. It's also worth noting that centrifugal compressors handle power surges better than axial compressors. Keeping some stages axial maintains better overall efficiency, since using only centrifugal compressors would drastically lower efficiency. Another disadvantage of centrifugal compressors is their large cross-sectional area. But since helicopter engines are usually at least partially hidden in the fuselage and don't create a critical drag penalty, this larger cross-section is less of a disadvantage. Because of the centrifugal compressor, air doesn't just flow straight rearwards into the combustion chamber like in conventional designs. Instead, the T700 uses a reverse flow annular combustor. Air flows outward from the centrifugal compressor, makes a U-turn inwards, then flows around the outside of the combustor and enters the combustion chamber through the diffuser holes where fuel is added and ignited. The hot gases then exit rearwards towards the turbines. This curved path does more than just redirect airflow. Air exiting the centrifugal compressor is moving fast and needs to be slowed down before combustion, otherwise you'd get poor fuel mixing and potentially flame blowout. The reverse flow design naturally diffuses and slows the air as it curves around, creating ideal conditions for stable, efficient combustion. This design not only allows for a more compact engine, but enables a modular construction where major sections can be removed and serviced independently, making maintenance in the field much easier. After combustion, the energy-rich hot gases expand rearward and spin the turbines, and you'll notice there are 4 of them. It's a free turbine system, meaning they aren't all mechanically connected. The first 2 turbine stages make up the gas generator turbine, which drives both the axial compressor stages and the centrifugal compressor. The rear 2 stages form the power turbine, which spins the output shaft that drives the helicopter rotors. The gas generator turbine uses about 75% of the total combustion energy to drive the compressors, while the remaining energy drives the 2-stage power turbine to turn the rotors. This configuration isn't exclusive to the T700. Many turboshaft engines use it, but plenty of other engines connect the turbine directly to both the compressor and the output shaft. The free turbine system has several key advantages. The most important is that each section can run at independent, optimal speeds. By having the gas generator spin at its optimum RPM, the engine is more efficient. But it also provides several operational advantages, like surge protection, so sudden load changes only affect the power turbine, not the gas generator. It also enables better auto-rotation capabilities, which is done during emergency landings, since the power turbine can rotate freely without having to drive the gas generator. It also enables a highly modular design, which is one of the T700's standout features. This increases maintenance access and reduces maintenance time, as major sections can be completely removed without having to remove the entire engine. Since most T700 applications are military, this provides massive benefits. The power turbine can also be fully replaced without having to change the whole engine. This dramatically reduces downtime and improves fleet readiness in combat zones. The trade-offs are slightly reduced efficiency due to losses between turbine sections, increased weight, more complex exhaust ducting, and higher manufacturing cost. Let's now jump back to the intake section and discuss a unique feature of the T700. The first compressor stage is axial, which has several rotors and stators and is more efficient than centrifugal compressors. But axial compressors are more sensitive to foreign object damage. With military helicopter applications operating in combat zones, this is a significant drawback as it increases maintenance requirements and failure rates. But General Electric came up with an innovative solution called an IPS, or Integral Particle Separator System. Air enters at what's called the swirl frame. This isn't a rotor, it's stationary with blades called swirl vanes. Its purpose is to swirl the incoming air in a helical pattern, like a tornado. This creates centrifugal force and separates the heavier particles like sand, ice, snow or debris from the lighter air. The centrifugal force throws the heavy particles outward while the clean air stays towards the center where it supplies the engine. It's kind of like swirling a marble around in a glass. The heavy marble gets pushed outward while the center is just clean air. The debris that gets flung outward is then extracted through a duct by suction created by a small, mechanically driven scavenge blower and expelled from the engine. At maximum power, this blower extracts about 15% of the total inlet airflow. So rather than using just simple filters or screens, the T700 uses a sophisticated air pre-cleaner. And this isn't just theoretical. During qualification testing, a T700 ingested approximately 35 kilograms of sand over 58 hours at maximum continuous power without significant power loss or engine damage. Taking it even further, 138 random objects like nuts, bolts and sockets were fed into the intake, and the IPS system separated 93% of these objects. I don't know about you, but feeding random solid objects into a turboshaft engine to see if it survives pretty much sounds like my dream job. Before I conclude with some final thoughts, let's quickly discuss the T700 model I've been using throughout this video. The kit arrived within 7 business days, well packaged and protected against shipping damage. Mine took a big hit, which put a hole in the outer box, but the inner kit box was perfectly safe thanks to bubble wrap protection. All required tools are included. I only reached for my own long nose pliers once, but it wasn't strictly required. Surprisingly, most engine parts are metal with just a few plastic components, resulting in a satisfyingly heavy finished model. Assembly took about a full day, though I did other things in between, and I'm definitely not fast at this type of thing. Even a pre-flight inspection takes me ages to finish, at the complete disgust of anyone flying with me. The instructions are clear enough that if I can do it, most people can. Some sections could be improved, particularly the electronics portion, but it was simple enough to figure out. I don't think I had any real difficulty during the assembly process, other than perhaps the fuel rail and injectors, which seemed overly finicky to fit. Building it component by component genuinely helps you understand this engine. Challenge yourself to identify every component and its function on the actual engine as you assemble it. It's a great test of your turboshaft engine knowledge. Overall accuracy is hard to assess since there are many T700 variants, but one area I'm unsure about is the gas turbine section. It spins in the correct direction, but has blades oriented like compressor blades rather than turbine blades. Compressor blades are oriented convex side forwards, facing the incoming air, and turbine blades have its concave side facing forwards. It was genuinely fun to build and looks quite good. It'll probably have a permanent spot on the shelf behind me in future videos. So, who is it for? Hobbyists, engine model collectors and students wanting to learn more about turboshaft operation. It's perfect for somebody like me who cares more about understanding overall operation and main components than absolute accuracy in every detail. I wouldn't recommend it for engineering professionals who need a 100% accurate scale model. If you're interested in getting one, use the code LetsGoAviate for a discount. Links and more details in the video description below. Now, let's get back to the real T700. Development of the T700 started in the late 1960s, evolving directly from the challenging operating conditions experienced in Vietnam. More than 25,000 T700s have been built so far, and beyond the dozen military helicopters it powers, it also drives fixed-wing aircraft like the Saab 340 in its turboprop CT7 version, as well as civilian helicopters like the Bell 214 ST. The T700 is still in production today, with new and improved variants continuing to be developed. However, by the mid-2000s, the ITTRIBUTION program was launched to find a replacement for the T700, which General Electric won with their T901 submission in 2019. So, do you think the T901 will become as iconic and successful as the T700? And what do you think of the T700 model I featured in the video? Let me know in the comments. Thanks for watching. See you in the next one.